Hello again. We're continuing our study of kinematics. Now, before I go any further, I just want to tell you that the answers for the questions at the end of the previous video happen to be here. So, okay. Anyway, let's move on. So far, we've been couching our discussion of the description of motion mostly in terms of the graphs. Now, here we're going to be talking about describing the motion in a more mathematical way. And I'm going to be giving you some formulas. And these formulas, they ultimately come from calculus, but at this point in your careers, most of you haven't had calculus yet. So I'm just going to give you the formulas and then let you use them. All right. So to begin with, let's consider the special case where there is no acceleration. The A is 0. Okay, so if an object has no acceleration, then it's not speeding up, it's not slowing down. The velocity is constant. If that's the case, then this formula right here will describe where the object is at any given time. So here's the formula. The position x is equal to x sub 0, which means the position when the experiment started, plus the velocity times time. Now, this 0 is coming from the fact that this is the position at time t equals 0. So that's why we call it x sub 0. It's the position when the time is 0. Okay. Now, if we make a graph of this formula, it's going to be a straight line graph. And the slope of this graph is going to be v. If the velocity is positive, it'll be a positive upward going slope. If the velocity is negative, if the object is going to the left, then the slope will be a negative going slope. And of course, if the velocity is 0, then it'll be a horizontal line because x will not be changing. All right, so let's have an example. I've got a trash truck and it's moving at 12 meters per second and it passes the 15-kilometer mark on a French highway. I picked a French highway because they have these nice concrete blocks every kilometer and so on. So anyway, okay, so then the concrete truck passes the 16-kilometer mark and then the 17-kilometer mark. Where will he be in 500 seconds? Well, actually, I gave you more information than you really need. Like, you didn't really need to know this piece here, the 16 and then the 17. That this is not very useful information. But you do need to know the 15 kilometers. Okay, so this piece of information is important because that's our x0. Okay, so now I'm going to be giving you all of these formulas, and in order to be able to use them, you have to match the information that you're given with the various variables and constants in the formulas. So we have that. Okay, so we're using this formula here, right? this is the formula we're using. And so, circle this, okay? So the V part of it, okay? Here, let's change color. This 12 meters per second matches up with the V. All right, that's why I wrote down V equals 12 meters per second. Okay, so when you're doing homework problems and you're stuck, or you're doing a quiz problem and you're stuck, this is a good thing to do. It's just to write down the pieces that you can match up. So we can match up that V is 12 meters per second. And okay, now I'm telling you that he passes the 15-kilometer mark. Okay, so that's going to match up with X0. Right? So these match up and these match up. And okay, so now we're ready to use the formula. We have X equals X0 plus VT, and X0 was 15 kilometers. Now, kilo, remember, is thousands, so I'm writing down 15,000 meters. Right? So in chapter 1, just as a reminder, I did say that when we're doing physics problems, one of the preliminary steps is to convert units to the standard physics units. So for example, we don't really want kilometers, we want meters. So you got to convert kilometers to meters. All right, well, K means thousand, so that's why it's 15,000 meters. 12 meters per second. All right, well, this is already in physics standard units, meters per second, so they're good. We just use that. So V is 12 meters per second, right? So VT, 12 meters per second, and T is, okay, the 500 seconds here, right? And that's another one of the ones that match up. That matches up with T, and okay, so these match up. And so, all right, so that's the 500 seconds there. And all right, so you put this into your calculator, and so 12 times 500 plus 15,000, and you get your answer, 21,000 meters. And since we're talking about a truck, we're talking about cars and so on, kilometers. In Europe anyway, we're always talking about kilometers and kilometers per hour. So I'm converting it back to kilometers. But you don't have to do that for this class. All right. Now, what's next? Well, moving on. What if the acceleration is not zero? That means that your object, your car, your rocket, whatever it is, may be speeding up, may be slowing down. Now, this could get really messy, really complicated, but we are going to make one simplifying assumption. We are going to limit ourselves. We're going to say that the acceleration is constant. So, yes, it's speeding up, but it's speeding up at a constant rate, or it's slowing down at a constant rate. So when you're doing these problems, you got to watch out. You got to make sure that if you're using these formula tools, that the acceleration is not changing. For the first few months of this class, that'll be true, okay? But at some point, you're going to have situations where the acceleration is changing, in which case, now things get even more messy. Okay, but for now, we're keeping things simple. The acceleration is constant. All right, so we have, in this situation, this nice formula here. And let's just read it out. So the position at any given time is given by x0, which is the beginning position, plus v0t. And v sub 0 is the beginning velocity, the velocity at time t equals 0. And then we add to this stuff 1/2 times the acceleration times the time squared. And this formula works. It will tell you where your object is at any given time. Now, if you make a graph, right, this is t squared. It's a quadratic. And when you graph quadratics, you get parabolas. So a graph of this formula will maybe have a parabola going upward. It could also be a parabola going downward, right? Maybe it's a negative acceleration. Okay. We'll be seeing that sort of thing happening in the examples. Now, there's another formula that goes with this right here. So this is telling us the velocity at any given time. So the velocity is equal to the beginning velocity plus the acceleration times time. And if you make a graph of velocity versus time, you're going to get this straight line. Actually, we saw this graph before, right, in the previous video. Okay. So let's have an example. So we have a character here who is speeding in her new Tesla car. And she goes through an intersection at 30 meters per second. And she's accelerating at a ludicrous 15 meters per second squared. The reason I use the word ludicrous is because the Tesla cars, when they happen to have various driving modes, and like there's the regular mode, and then there's the sport mode, and then there's the ultra sport mode, and on the whatever, in the controls they call it the ludicrous mode. Okay, so Teslas are pretty fast cars. All right, anyhow, what is her position and velocity after 5 seconds? Okay, so what is her position? So that means we're going to be using this formula here, right? And we need to do some matching up. So 30 meters per second is, I think that's the beginning velocity, right? So we're going to match V0 with 30 meters per second. And this is an acceleration, right? Meters per second squared. Okay, so that's easy. That's going to match with the A, all right? So here we go. And 5 seconds, well, that's going to match with the T, right? Now, notice that T comes up twice in the formula, right? There's a T here, and there's a T which is squared here, right? So there, this is T. Okay, got too many lines going every which way. Okay. Now, I didn't actually say what x0 is, but when you have a problem and something like x0 is not specified, as you do these problems, you'll begin to get used to it, and you'll realize, okay, well, you didn't say what x0 is, but after doing a bunch of these problems, you realize, okay, well, that just means that it's 0. So we're going to assume that x0, the initial position, is 0 meters. And then okay, so here we've done this first step. We've written down the pieces of information. We've matched them up. So now we plug in. And so we have x equals x0, which is 0, plus v0 times t. All right, here's v0, here is t, 5 seconds, plus 1/2 at squared. All right, here's the half, here is the acceleration, the time squared, 5 seconds squared. It's really easy to forget the squaring. I do it once in a while and mess up. Please try not to mess up. And you put it into your calculator and you get the answer, 3,375 meters. So, this car is really going fast, right? After 5 seconds, it's gone 3.375 kilometers. It's gone 2 miles in 5 seconds. Wow. Okay, I hope she doesn't have an accident. Okay, now there was another piece to the question. It said, what is her position and velocity? Okay, so we need to do the velocity part of it. Let me erase some of this stuff here. Erase this line, erase this, erase this here. Okay, so we have the velocity formula here. V equals V0 plus AT. Now, V0 is the 30 meters per second. Right? And the A is the 15 meters per second squared. And the 5 seconds is the T, right? So the T is the 5 seconds. Okay, so we're gonna, you're gonna write these down. And okay, so first step, T is 5 seconds. So you wrote it down, and now we start plugging it in. So we have V equals V0 plus AT. Here's V0, 30 meters per second. Here is the acceleration. Here is the time. And you do the math, and you get the answer, 105 meters per second. Our next topic is falling. When an object falls under the influence of gravity, it accelerates. The acceleration is constant, and it'll keep going faster and faster and faster unless air resistance, air friction gets in the way. So there's always going to be a little bit of air resistance. So technically, what we're about to discuss is an approximation. But if you're talking about a rock or a boulder or something with high density, then the effect of air is tiny, and we can ignore it. Okay, so if I drop a rock, it will accelerate, and it will go downward faster and faster, and this will be an acceleration. It'll be 9.81 meters per second, which we write meters per second squared, in the downward direction. Here it's 3 significant figures, 9.81. Actually, most books will just put 9.8, dropping the 1, and some books will round this to just 10. The reason being that it just makes the math easier, it makes the homework a little less tedious, and so on. It's also worth pointing out that the downward acceleration of gravity can actually change from place to place. So if you're at the top of a mountain, or if you're deep down in a mine, deep underground, it could deviate from 9.81. So this is just a kind of a typical acceleration for places at sea level. All right. Now this acceleration comes up over and over again so often that instead of calling it A, we've given it a special letter. We've calling it G for gravity. Okay. Now, so let's take a look at an example. If I drop a rock from a cliff, then its position will be x equals minus 1/2 g times the time squared. So g is the acceleration, 9.81, but in fact the acceleration is downward, and so that we've added this negative sign to say it's downward. So g, the convention is to say g is just a regular positive number, but since falling is a downward acceleration, we then add a negative sign later on here. So, okay, now this is a quadratic, right? It's t squared. So if I make a graph of the position of the rock, um, here we've this is the instant at which we drop it, and as the time increases, the position of the rock becomes more and more negative, which makes sense, right? It's falling in the downward, it's falling in the negative direction. This number here, 4.905, I got that by taking 9.81 and dividing by 2. And so it's 1/2 of 9.81. Also, we have that the velocity of the rock is given by v equals minus gt. And if I make a graph of that, time and velocity on the vertical axis, then this is when I let go of the rock and its velocity increases linearly with time. It increases in the negative direction, so it's becoming more and more negative. Yeah. Okay, so just some quick examples. We have a scenario here. The rock starts right as it leaves my hand here. Its position is 0, so this height right here I'm saying is position x equals 0. And the experiment starts at that instant, so the time is 0, and I'm not throwing it upward or downward, so its initial velocity is 0. And maybe we could ask, where is this rock going to be at 2 seconds, right? What will x be? And what will be the velocity? And okay, well, that's easy to do. You plug into the formula. So we put in 1/2 times 9.81. I left the units out. That should be meters per second squared. Times 2, I left out the units again. Seconds, right? 2 seconds. Square the whole thing. And we get our answer. So it will be down 20 meters, or to be more accurate, it'll be down 19.62 meters. What about the velocity at 2 seconds? So we plug into to this formula here, and so we have minus 9.81 meters per second squared times 2 seconds, which gives, it's a little bit cut off, negative 19.62. I think that's what it should be here, 19.62. And the units will be meters per second. So, okay, so a little reminder here, keep in mind that gravity problems are the same as constant acceleration problems. They're just like all the problems before. It's just that the acceleration is minus g, minus 9.8 or minus 9.81. And yeah, okay, over here, I'm just saying what I said earlier, that a lot of books will round to 9.8 or even to 10 to make the math easier. Okay. Now, in the previous discussion, I was saying I'm just going to drop my rock, but I could toss the rock upward, and in which case the initial velocity of that upward toss, that'll become v0, right? That's the beginning velocity, and the experiment still starts at height x equals 0, and the experiment starts at time 0. Now, what that will look like in a graph is like this. You're going to have x becomes v0, the initial velocity, that upward toss, times t, minus 1/2 gt squared. And if I graph that, it's still a parabola, but the parabola goes up and then it comes back down. And right here at the top, that's the time when the rock stopped going up, and for an instant it is motionless, and then it begins to fall. And yeah, okay, and I'm plugging in g here, minus 1/2 g, so this becomes v0 times t minus 9.81 times the time squared. And the velocity, here's our new velocity formula. V equals the initial velocity, which is the upward toss, minus gt. And so if I graph that, it's the same as before, but my line has been shifted up by the v0 amount. And so you start off with a positive v0, and as time goes on, the rock is going slower, 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 and then right here it's actually stopped, and then it's beginning to go faster, faster, faster in the downward direction. Okay, and here's our formula, v0 minus 9.81t. So let's have a real simple example where we plug in some numbers. Let's suppose that the initial velocity was 3 meters per second upward. What will the position be after 2 seconds? So it's going to go upward, and then the clock is ticking, and then it's going to start coming down. And I don't know whether it's going to turn around before or after the 2-second time, but we're about to find out. So we plug in. Okay, so I'm using this formula here, right? So this formula here is getting used right here. So V0, we said, is 3 meters per second, and the time is 2 seconds. And then I have minus 1/2 g, which is 9.81 times 2 seconds squared. And I put this all into the calculator, and I find that it's down in the negative region. So it's somewhere, I don't know, maybe somewhere way down here, because it's actually pretty far down now. And so there we go. So it turns around, and then it starts to speed up downward, 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 and at 2 seconds, it's already gone down pretty far. What about its velocity at 2 seconds? So we're going to use this formula here, and it's getting used. And so I put in V0, which is 3 meters per second, minus the gravity number, 9.8 or 9.81 meters per second squared, times the time, 2 seconds. And we find that it's moving along already pretty fast downward at 19.6 meters per second. So downward, that's why there's a negative sign, minus 19.62 meters per second. In the discussion that we just had regarding describing the motion of something that's falling, there was an assumption that was being made, and that is that air friction or air resistance could be ignored. That's why I picked a rock, right? Generally, rocks are pretty massive, and they fly through the air without the air really doing anything to the rock. But sometimes the air actually does have a big effect. And so I'd like to show you that situation. So first, what I'm going to do is I'm going to drop something that's massive. It's not quite as massive as a rock, but the air won't have any effect. And then I'm going to drop something very light, and the air has a dramatic effect. So let's make it happen. So, right, first, the spool of wire, which is massive, and the air resistance won't have much effect. And it accelerates downward at 9.8 meters per second squared. But this paper filter, if I let it go, doesn't accelerate. The air resistance, it prevents it from exceeding a certain speed, and so it falls at a nearly constant rate.